Okay, this is 6.3, the binomial model. So number one, the normal model applies to many real-life continuous, gotta get the pen turned on, continuous numerical variables. The model most commonly used for discrete numerical variables is the binomial probability model. So it's an important reason for distinguishing between whether or not a variable is continuous or discrete, because we're going to be using a different model for each one. Okay, so number two, the results of a random experiment may be modeled by the binomial probability model if the outcomes you are interested in are counts. The following four characteristics must also be present. So there must be a fixed number of trials. Number of trials is represented by the letter n. Only two outcomes are possible at each trial. These outcomes are referred to as a success or as a failure. 3, the probability of success is the same in each trial. The probability of success is represented by the letter p. And 4, the trials are independent. The outcome of one trial does not affect the outcome of any other trial. So an example of a random experiment that can be modeled by the binomial probability model is rolling a fair, this is important, fair six-sided die 6 times and recording the number of ones. So our first requirement that there's a fixed number of trials has been met because we're rolling the die 6 times. So we're doing rolling the die 6 times. We didn't specify that. We might not have a fixed number of times or trials. And the second one, there are only 2 outcomes possible at each trial. So we're going to call a success rolling a 1, and a failure then can be rolling any of the other numbers. So even though the die has 6 things that can happen, we're grouping some of those together to fit this requirement, 2 possible outcomes. And again, since we were interested in recording the number of ones, that's what we're going to call our success. All right, fourth thing, the probability of success is the same in each trial. Because the die is fair, we can say that probability is 1 out of 6. The chance that you roll a 1 is 1 out of the 6 things that can happen. And then the last thing, trials are independent. Well, the outcome of one roll does not affect the outcome of any other roll. So if I roll a 1 the first time I roll the die, it's not going to have any effect on what appears the second time I roll the die. All right, a second example, number 4. A second example of a random experiment that can be modeled by the binomial probability model is flipping a coin 2 times and recording the number of heads. So we're going to flip a coin twice, and we're going to record the number of heads. All right, so first requirement, there's a fixed number of trials. In this case, n is 2, and we're flipping the coin twice. So we've met that requirement. All right, the second one here, there are only 2 outcomes possible at each trial. In this case, we were calling the success heads because that's what we were interested in. A failure then is everything else, which in this case is just tails. All right, the third thing, probability of success is the same in each trial. This is a fair coin. We're going to say that that probability is 1/2, and it's the probability of getting heads when you flip that fair coin. All right, and then the last thing, fourth requirement, the trials are independent. The outcome of one toss or one coin toss is not going to affect the outcome of any other toss. That's important, but we can check that one off. That one's been met. Okay, and number 5, another example of a random experiment that can be modeled by the binomial probability model is flipping a coin 4 times and recording the number of heads. This is really similar to what we just looked at on the previous page, but the number of trials is going to be higher. So notice we have n equal to 4. Notice we still only have 2 outcomes possible. We either get heads, which is what we're going to call a success, and a failure is tails. Probability of success is the same in each trial. It's still 1/2. We're going to again assume that the coin is fair. And last piece, the trials are independent. So again, the outcome of one coin toss is not going to have any effect on the outcome of any of your other coin tosses. All right, so we have the sample space listed below. So it says the following sample space lists the outcomes for this random experiment of flipping a coin 4 times. Use the sample space to complete the table of the probability distribution below. So again, here's our sample space. And it lists all the outcomes for flipping a coin 4 times. So notice there are 16 outcomes. Okay. All right, so let's take a look. Number of heads is 0. If we look, that only happens once. So that's right here. So our probability is 1 out of 16, which is 0.0625. All right, probability of getting one head. Let's see, that's here. Oh, nope, sorry, that's two heads. Let's look for one head. That is right here, here, and here. I think there's one more right here. So that happened 4 out of the 16 times, or 0.25. And then let's look at the next one. So we got two heads. That is right here, here. Oops, and I missed that first one. Here, here, and here. There were 6 of them. So 6 out of 16, which is 0.375. And then let's see, what else do we have? I'm going to look at 3 heads. So 3 heads is right here, here, and here, and here. So that happened 4 out of 16 times, or 0.25. And the last one, 4 heads, there should just be one left, right here. So that was 1 out of the 16 outcomes, so 0.0625. Okay, so we've got our probability distribution given here. So again, remember that that's listing possible outcomes when you flip a coin 4 times, and the probability of each of those outcomes. Okay, so check. What do these 5 probabilities add up to? I'll let you grab a calculator and press pause, and verify that you get all 16 outcomes accounted for, or 1, if you add up your decimals, which means we've accounted for 100% of what can happen, 100% of the outcomes. All right, next thing, we're going to use these probabilities to complete the graph of the probability distribution below. So notice the axes on the left, the vertical axis, is labeled as probability, and the horizontal axis is the number of heads. So for 0 heads, we had a probability of 0.06, so right about there. 1 head had a probability of 0.25, halfway between 2 and 3. Probability of 2 heads was 0.375. And probability of 3 heads was 0.25. And probability of 4 heads was 0.0625. Okay, number 6, the binomial distribution depends only on the values of n, which is your number of trials, and p, the probability of success. So we have notation for this. It's b for binomial, n for the number of your trials, p is for your probability of success, and x is going to count the number of outcomes or successes you're interested in. So this notation is used to represent the binomial probability of getting x successes in a binomial experiment with n trials and probability of success p. So the notation for our previous experiment, again, here's the b for binomial, 4 coin tosses, probability of getting heads was 0.5. This is somewhat generic right now because we didn't specify a value of x. So in the second bullet, we have an example. If we want to know what's the probability of getting 2 heads, so we're saying x is 2, then we replace x with 2 in that notation. And then we can say what the answer is. If we go back to our table, we'll find that that happened 6 out of the 16 outcomes, or 37.5% of the time. Okay, number 7. Once an experiment has been identified as binomial and these values have been defined, you can find any probability you wish with one of the following options. So you can use the outcomes in the sample space. You can use the graph of the binomial probabilities. You can use technology such as StatCrunch. You use a table of probabilities, and there's a copy of these tables in the back of your textbooks. Or you can use a formula. And keep in mind that we will not be using this formula in this class. So part E, I'm giving that to you because I know some of you may have seen it in the past. But keep in mind that if it's shown in my math lab, or my math lab says something about using a formula, you don't need to use this. Use StatCrunch or use the table. So these are the 2 things we're going to rely on the most, table and technology. Okay. All right, so next up, by the way, these will be given to you on the test. So table is probably the most important because the table will be provided on tests. And if you check your formula sheet, you're going to see that the formula given here is not even included. So again, don't need to worry about that. All right, number 8. Okay, let's use these first 4 methods to find the probability of getting one head when a fair coin is tossed twice. So first up, let's look at our sample space. And the hint here is there's 4 outcomes. So our sample space, if we flip a coin twice, we might get both tails. We might get tail and then heads, heads and then tails, or we might get both heads. So here's our sample space. So that, using that, we can then complete the following probability distribution. So if we look, the number of heads, if that's 0, that only happened 1 out of the 4 times, so there's a probability of 0.25. Getting one head happened twice, so that's a probability of 0.5, happened 2 out of the 4 times, or 2 out of the 4 outcomes. And getting 2 heads just happened once out of the 4, so it has a probability of 0.25. So notice that the sum of these probabilities is equal to 1 or 100%. So we've accounted for everything that can happen if you flip a coin twice. All right, so what's the probability of getting one head when a fair coin is tossed twice? Since we can use the binomial model, let's use our notation. We have B for binomial. We had 2 tosses, so 2 trials. Probability of success for getting heads was 0.5. We're specifically interested in one head, so X is 1. And from our table, we now know that that's 0.5 or 50%. Here's the probability that that will happen. So that comes from right here. Okay, just a note, this number again is our value of X. All right, the second option, use a graph of the binomial probabilities. So we've got that in part B, so use the following graph of the binomial distribution to confirm your probability from part A. So here's X equal to 1, and that line above that has a height of 0.5. So again, we have that 50% or 0.5 right here. We're just using a different method to confirm that. And by the way, this was created in StatCrunch. And this vertical axis here, missing a label, but it should say probability if you want to fill that in on your papers. Okay, in part C, the following is output from StatCrunch. So we're going to use this to get the probability of getting one head. So notice this graph here looks just like part B, but we have this added information from StatCrunch as well. And so this is something that you can do on, you'll probably be doing this in your group activity today, but you can change this here. So right now we were looking for the probability that X is 1. You can use this drop-down menu, that arrow there, to change that to a less than or to a greater than sign. So you can manipulate this and get different probabilities. You can also enter a different number into here. So if you wanted the probability that X is 2, you can make that change there. And then our probability is given right here. So this is again confirming what we got from the previous 2 methods, that the probability of getting one head when you toss a coin twice is 50%. So again, using that notation, we had 2 trials. Probability of success is 0.5 or 0.50. There's in one head, and we just found that that probability is 50%. All right, so note you're going to get more practice with this feature in today's group activity. All right, and then D, the following is an excerpt from Table 3, Binomial Probabilities, and it's from the back of your textbook. It's also in the back of your packets. Oops, back of packets. So double check that you have a copy of this. Again, you're going to need that from your homework. And you definitely want to know how to use that because you're going to be given that on your test as well. All right, so we're going to need to use the rows of values that correspond to n equal to 2 trials. So notice the first column is labeled with n, and it starts with n equal to 2. We then need to find the row corresponding to x equal to 1 success. So here's x. So if we go down, here's the row for x equal to 1 success. And then we want the column for probability of success being 0.5. So here's p. Here's p equal to 0.5. And you're going to figure out where all of this kind of overlaps. So here's a success of 1, or I'm sorry, 1 head. And then in this column, there's that 0.5 that we calculated above. So the probability of 1 head when a fair coin is tossed twice is 0.500, or again 50%. Okay, number 9, what would happen if we changed the number of coin tosses or the probability of success? Well, for different values of n and p, we'll have different binomial experiments, and that means the binomial distribution looks different in each case. So in our first example, we're going to compare the binomial distribution for flipping a fair coin twice. Notice our number of trials is 2. And the binomial distribution for flipping a fair coin 4 times. So n is 4. Notice in both of these, probability of success is 0.5. And for now, we're leaving x undefined. So we're leaving open the possibility of what x can be. So how are these two distributions similar and how are they different? So again, 2 coin flips is there, 4 coin flips is there. So you may want to press pause for a moment, jot down some notes to yourself, and press play when you're ready. What you're going to find is that in both cases, the shape is unimodal and also symmetrical or symmetric. The centers are different. The center here is at 1. Here the center is at 2. Some of you may notice, though, that the center is half of the number of outcomes. Same thing here. The center is at half the number of outcomes. So they're similar in that regard. All right, our second example, we're going to compare the binomial distributions for flipping a fair coin 10 times when the probability of success is 0.5 and when the probability of success is 0.1, so we don't have a fair coin in that case, it's weighted, and also when the probability of success is 0.9. So again, we want to look at how are these distributions similar and how are they different. So keep in mind before you get started that this is the binomial distribution when the probability of success is 0.5. This is the binomial distribution when the probability of success is 0.1. And down here, this is the binomial distribution when the probability of success is 0.9. All right, so if we look, notice that this is the only one that's unimodal. It's the top left and symmetric. And these two are different in terms of their shape. This one is skewed right. And this one is skewed to the left or skewed left. So if you look more closely here, there's more likely to get a lot of failures. Which another is saying you're more likely to get tails. You only have a 10% chance of getting heads, well then you have a 90% chance of getting tails. Here you're more likely to get a lot of successes, which means you're more likely to get heads. And since we labeled a success as heads. So keep in mind that the probability of a success is going to play a role in the shape of these distributions. A binomial distribution can be described by its center or mean and its spread or standard deviation. Mean tells us where the distribution balances, and the standard deviation tells us how far values typically are from the mean. So what do you think the mean is for each of the following distributions? So again, press pause, give this a try first, and then press play again. Here on the left, it looks like the mean is probably 1. It looks like the balance point or center of that distribution. And over here on the right, it looks like that the mean is probably 2. Again, that looks like the center of the distribution or the balance point of that distribution. Again, just notation, just good review. This is a binomial distribution when you have 2 trials. Probability of success is 0.5. And here, this is the binomial distribution with 4 trials. Probability of success, 0.5. All right, and the third one, the following binomial distribution, notice is skewed to the right, so its tail on the right is longer. Estimate the mean of this distribution. This one's a little tougher to do, but maybe a good guess is that the mean is around, let's say, maybe about 5. Okay. All right, again, this is a binomial distribution when you have, let's see, 15 trials. Probability of success is 0.3. That's given down here, too. All right, in number 11, the mean mu of a binomial distribution can be found with the following formula. And that's, notice our symbol here, mu, the Greek letter mu for mean, is equal to n times p. So the number of trials times probability of success. And this is given to you on your formula sheet, so there's no need to memorize this. All right, so this formula gives us the mean number of successes, or a typical outcome in a binomial experiment. This value is sometimes called the expected value, since it's the number of successes you would expect if a random experiment were repeated n times. So we're going to finish up this page by using this formula to calculate the mean of each of the above distributions. All right, so if we come up here to the top left, using that formula, which is that the mean is equal to n times p, we have the mean equal to 2 times 0.5, which is 1. So it matches our expectations from what we did before, our estimate. We do this on the top right, and the mean is equal to n times p. So the mean is equal to 4 times 0.5. We again confirm what we had from our estimates originally. And then the third one that was a little bit tougher, this will be interesting to see how good our estimate was. We have that the mean is equal to n times p. So the mean is equal to 15 times 0.3. And that gives us a mean of 4.5. So we're a little off in our estimate. We had 5 originally, so it looks like the mean is right here at 4.5. Okay, the standard deviation sigma, that's your Greek letter sigma, of a binomial distribution can be found with the following formula. And notice that it relies on n and p as well. And also keep in mind this is on your formula sheet. So again, no need to memorize it, just need to understand how to use it. All right, so we're going to use this formula to calculate the standard deviation for each of the following distributions. And these distributions are the same as number 10, previous page. Well, the standard deviation is a little harder to estimate, so we didn't do that on the previous page. But we'll calculate it now. All right, so this is going to have a standard deviation equal to, that n equal to 2, p equal to 1/2 or 0.5, and we're going to do 1 minus 0.5. And again, press pause, try this out on your calculator, but you're going to get an answer of roughly 0.7071. And so again, on average, typical distance from the mean, remember our mean was 1, here was mu. On average, our other outcomes are about 0.7 away from that. And again, an average means that some are going to be a little closer, some are going to be a little bit further away. So we've got the ones in the middle that are closer, and then the 2 and the 0 that are further away. All right, our second one, using this formula again, we got n equal to 4, p equal to 0.5. And again, press pause, try this out, but you should get a standard deviation of 1. And so again, what that's telling us is that on average, a value is about 1 away, so typically 1 away. So we've got some that are closer. The 2s are obviously closer to the mean than anything else. 3 and 1 are just 1 away from the mean. And then we've got a few on the end that are a little further away from the mean. So again, this is a typical distance of an outcome from the mean. All right, and then the last one, sigma is going to equal 15 times 0.3 times 1 minus 0.3. And again, press pause and verify this, but you should get a standard deviation of about 1.775. So remember, our mean for this one was at 4.5. That's the previous page. So here's our mean. And our standard deviation is just giving us a typical distance of an outcome from the mean. So an average of about 1.8 away from the mean. And notice we've got a lot that are pretty close to that, but we also have some that are further away. Okay, so the most common application of the binomial model is in survey sampling. So imagine a large population of people, such as 100 million registered voters in the U.S. Let's assume that 50% of them will vote for the Democratic candidate in the next presidential election. Suppose ABC News takes a random sample of 100 registered voters and asks them which candidate they are going to vote for in the next presidential election. All right, before we can use the formulas for the mean and standard deviation of a binomial model, let's make sure that the 4 characteristics of the binomial model are satisfied. All right, so fixed number of trials. Note that we were going to talk to or sample 100 registered voters, so we can say yes, there's 100 voters that we're going to look at, so 100 trials. There are two outcomes. Yeah, they can either vote for the Democrat or the Democratic candidate or somebody else, or we can say or not. So there's our two choices. Probability of success is the same in each trial. We were told that there were 50% that would vote for the Democratic candidate. So if we imagine taking a name out at random from a hat, we'd have a 50% chance of pulling out a voter that's going to vote for a Democratic candidate. And then the trials are independent. We're going to say yes, and that means that one person's vote or any person's vote is independent of the other voters. So one person's vote is independent of the other voters. All right, so let's use the formulas for the mean and the standard deviation of a binomial model to answer the following questions. So first question, how many registered voters in this sample should we expect to vote for the Democratic candidate? Because that's really asking for the mean or expected value. So if we plug in our values, we've got n is 100, p is 0.5. That tells us to expect 50 voters to vote for the Democratic candidate in our sample. All right, give or take how many is really our standard deviation. So roughly how far away do we expect our answer to be from the mean? So we're going to take square root of n times p times 1 minus p. So in that case, this is 100 times 0.5 times 1 minus 0.5. And that gives you a standard deviation of 5. So we would expect about 50 voters, give or take 5. And so sometimes you may see that written as 50 plus or minus 5 voters. We know we're not necessarily going to get exactly 50 each time. Right, and then would you be surprised if 60 registered voters in the sample indicated they would vote for the Democratic candidate? And how about 70? So let's start with 60 voters. All right, so I would argue that we would not be surprised to get 60. If you look more closely, that's because 60 is only 2 standard deviations above the mean. So we can say that's 2 standard deviations above mu. And we know from past experience that that happens. All right, for 70 voters, this one we might say, yeah, we'll be a little surprised. So we'll say yes for this one. And the reason for that is 70 is, let's see, that looks like 4 standard deviations above. And that's something really unusual. To be 4 standard deviations away from the mean, or in this case, above the mean. That's unusual. Okay, so keep in mind that typically surveys refer to the percentage of voters rather than the number of voters when they report the results in the news. The binomial distribution still applies since we are just converting the counts to percentages. Right, so for example, we take what we got above. Remember, we were expecting about 50, give or take about 5 voters. And in the news, what we would find is that this would be converted to 50 out of the 100 people, or 50%. Give or take 5 out of the 100 voters, which is 5%. Okay, so again, this is telling you number of voters, which is what our binomial model gives us. But typically we see it converted to percentage of voters.